So now that we've gone through sum and differences, the natural question, right, is what can we do with products, right? And our first instinct, right, is this, right? That d dx of f of x times g of x, well, that is f prime of x times g prime of x, right? That's our first instinct. So let's check if it's true, right? Let's say f of x equals x and g of x equals 2x, okay? And I want to make it clear this is our guess, right? Well, so what happens with this, right? Let's take the derivative both ways, right? What's f prime of x times g prime of x, right? Because we can take the derivative of each of these functions. Well, okay, f prime of x is going to be 1, and g prime of x, sorry, let's have g of x be 2x squared, okay? G prime of x is going to be 4x's, right? The 2 drops down, giving us a total of 4 as our coefficient, and 2 minus 1 is 1. And so that's going to just come out to 4x. Okay, so what if I multiply and then take the derivative? So d dx of f of x g of x, that's my derivative of, it looks like 2x cubed. And when I take the derivative of 2x cubed, I'm going to get 6x squared, right? Our 3 drops down, multiplies by our 2, and 3 minus 1 is 2. And these, unfortunately, are different. So that means that the product rule, or our initial guess at the product rule, was not quite right. We're going to omit a proof of the product rule. There's one in the book. I recommend you take a look at it. It has a few handy tricks that might help your math muscles train a bit. But this is what we get, okay? And actually what I'm going to do is I'm going to color code our f and our g, okay? When you take the derivative of f of x times g of x, here's what you get. You get f prime of x times g of x without a derivative, plus f of x times g prime of x, right? So you take the derivative of the first one times the second, plus the first one times the derivative of the second, okay? And this is one that we will use all throughout the quarter, and so we ought to get used to it, okay? And the best way to get used to these sorts of things is to run a few examples, okay? So let's say, for instance, we're trying to calculate the derivative of this guy. Say f of x is 2x squared minus 1 times x cubed plus 3, okay? And you might think right away, well, I can just multiply those together and then use what we had before. And that is true, but a little bit later in this lecture, we'll meet a couple of functions that you can't quite do that with. And so it will help us to work on these to make those other ones a little bit easier, okay? So in this case, right, this is one of our functions, and this is the other, right? So we're going to get the derivative, 2x squared minus 1, times x cubed plus 3, plus 2x squared minus 1 times the derivative of the second, x cubed plus 3. And we can work these through, right? The derivative of 2x squared minus 1, our 2 is going to drop down and we're going to get 4x's. Our minus 1 is just going to drop. Then we're going to have x cubed plus 3. Then we're going to add to that 2x squared minus 1. And then what's this derivative? Our 3 is going to drop down. We're left with 2x's. And then once again, this 3 just drops because the derivative of a constant is 0. Distributing in, it looks like we're going to get 4x to the fourth. Looks like plus 12x's. And we're going to add to that, looks like 6x to the fourths minus 3x squared. And simplifying a little bit further, 10x to the fourth minus 3x squared plus 12x's at the end. Okay, and then I realized I'd forgotten to write that we were calculating f prime of x. These two functions are obviously not equal. Okay, let's take a look at one more of these. Let's say g of x is x cubed times the square root of x plus 1. Okay. Once again, if we want to calculate g prime of x, we need to take the derivative of the first being x cubed, times the second, plus the first, which is x cubed, times the derivative of the second, the square root of x plus 1. Okay. Working this out, we see that the derivative of x cubed, we've seen this before, is 3x squared times the square root of x plus 1. Then we're adding to that x cubed the derivative of the square root of x. The square root of x is x to the 1/2, right? So if we're trying to take the derivative of x to the 1/2, our 1/2 is going to come down, and we need to subtract 1. 1 minus 1/2 is negative 1/2, right? So that's what we get left over with multiplying by this guy, okay? And then, of course, as per usual, the derivative of this constant is just 0, okay? Distributing this in, we're going to have 3 times x squared times x to the 1/2, or x to the 5/2. And we're going to add to that 3x squared, okay? And then what happens over here? Well, distributing in this x cubed, we're going to have, it looks like 1/2 x3 minus 1/2 is once again 5/2. 3 x to the 5/2 and a half x to the 5/2 is going to leave us with 7/2 x to the 5/2 plus 3x squared, and that is our derivative, okay? So we've done sum and difference, we've done product, and now the natural next step is to investigate what happens when you look at the derivative of a quotient, okay? And what should happen here, right? You know, our guess, I guess I should say that we're talking about the quotient, okay? Once again, here's our guess, right? Is that d dx of f of x over g of x would be f prime of x over g prime of x, right? This would be so nice. It would be so nice if this were true. You can take the derivative of them individually, right? That's how it works with limits. But unfortunately, that is not quite the case, okay? Once again, let's take two functions. Let's say f of x equals x cubed and g of x equals x squared. Do this process and do this process and see if they agree, right? Let's start with the derivative this time. So d dx of x cubed over x squared. Well, that's the derivative of just x, right? And then, of course, the derivative of x is 1, right? So 1 drops down, 1 minus 1 is 0, and x to the 0 is 1. Okay, well, what if we take our derivatives first? What's f prime of x over g prime of x? F prime of x is 3x squared. G prime of x is going to be 2x, and we get 3 over 2x. Once again, these are different, so our guess is unfortunately not correct. Okay, that guess was wrong, and we need to find out what the actual quotient rule is. Okay, and the quotient rule looks a little bit something like this. If we're taking the derivative of f of x over g of x, okay, I'm going to write it out, and then I'm going to tell you a little bit about it. So it's g of x times f prime of x minus f of x g prime of x over g of x squared. Okay, and this quotient rule is famous for a number of reasons. Of course, one of the reasons that it's famous is it's ridiculous, right? It is not intuitive. This isn't what you would guess it would be based on even how the product rule looks, right? And one of the other reasons that it's famous is that almost everyone who teaches calculus has a little song that they sing to teach you the quotient rule, okay? And the song that they sing is always the song that their calculus teacher sang when they were teaching, or when they were learning calculus for the first time. And unfortunately, there's two problems with that, one bigger than the other. The not very big problem is that I am a very, very poor singer. Now, I'm more than willing to embarrass myself for the sake of teaching math. So if I did have a song to sing, I would. And here's the second problem, which is perhaps a little bit bigger of a deal. Is that when I was a calculus student, I was gone on the day that this was taught. And so I never inherited a quotient rule song from my calculus teacher. And so I can't pass one on to you guys. He posted his lecture notes online, so I took a look at them, and he wrote the lyrics of the song, right? And here were those lyrics written at the bottom of his lecture notes. Okay. He wrote low, D high, minus high, D low, all over low, low. Okay. This is how it was presented to me, without tune, without melody, without anything. And this tells you what to do. You write low, you take the derivative or D high minus high D low all over low 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 squared. Again, I have no idea how he sang this. And then that combined with the fact that I am, as I said, a terrible singer, what I did to memorize it was I memorized this: low, high, high, low, low, low. Where in memorizing that, right, I also had to remember that there's a minus, and that you're taking the derivative of the second one. Now, if you want to put this to music and add a little melody to it, absolutely go right ahead. I have, as I said, I have no idea what other people's melodies are. Everyone that I've talked to has given me a different one. And so, as weird as it stands, I guess I'm creating a generation of calculus students who also don't have a song to go with this. But also, I suppose if you put this to your own melody, you are more likely to remember it. Um, and if anyone has any melodies that they feel fit particularly well, send me an email, and then maybe I can incorporate that in the future. Okay, so wild math stories aside, let's do an example of this. Okay, so let's say we're trying to find the derivative of something like x over 2x minus 4. Okay, this is our high, this is our low, right? So if we're trying to find the derivative, we're going to have low d high d dx of x minus high d low 2x minus 4 all over low low. Okay, and so our 2x minus 4 stays. The derivative of x is just 1, right? And then we're left with x. And then for the derivative of this guy, the d low, our 4 is going to drop, this x is going to drop, and we're just left with the 2. Okay? Over low, low. And this guy cleans up really well to just minus 4 over 2x minus 4 squared. Okay? The quotient rule looks pretty scary when you're introduced, which is perhaps why many teachers and professors introduce a song along with it. But I think once you kind of start jumping into it, it's not all that bad. Okay, for this one, we're going low d high, so x squared minus 1, d dx of x squared plus 1 minus our high, which is x squared plus 1, times d low, low high, high low, over low low. Okay. And what happens next? Right. Well, x squared minus 1 stays the same. Our x squared plus 1, when we take the derivative, the 1 is going to drop. The x squared is going to give us a 2x minus x squared plus 1. And actually, the same thing happens here, right? We just get a 2x, and our minus 1 drops. And then we're doing this over x squared minus 1 squared. And let's start the cleanup, right? Distributing in this 2x, looks like we're going to get 2x cubed minus 2x minus, looks like 2x cubed again, minus 2x, right? All over x squared minus 1 squared. My 2x cubed and my minus 2x cubed are going to cancel. Looks like we're left with minus 4x's over x squared minus 1 squared. Okay. We'll do one more of these before moving on to our last rule. Okay. And that's going to look like this. Let's say h of x is the square root of x over x squared plus 1. Okay, a little bit scarier since we have this square root where we're going to deal with a weirder scenario because we're going to have some fractions. But we can move forward just the same as long as we go back and make sure we actually wrote what we were calculating. Okay, so we can trudge through, unfortunately without the aid of music and a song to sing, but again, I encourage everyone to sing their own little melody right there. Okay, we're going to have low d high minus high d low all over low low. Okay, and let's sort of work this through a bit at a time. X squared plus 1, we already saw the derivative of this guy, right? It's 1 over 2 times the square root of x. You'll most likely encounter the square root of x and taking the derivative of it more than you expect. So I would encourage you to memorize this and also know where it comes from, right? It does us no good to just memorize math when we don't know what we're actually doing, right? We're going to subtract from this high, taking the derivative of the low. Looks like we're just going to get 2x because our 1 drops, and then divided by low low. And let's see if we can simplify this at all. Instead of multiplying this guy in, and this may seem a little bit strange, but what we can actually do is factor out a 1/2. I'm going to write it like this to make it a little bit more obvious what we're doing. We're going to factor that out of our numerator, right? That's exactly what we have here. So it's just left with an x squared plus 1. But what happens when I try to factor that out of here, right? When I pull out an x to the negative 1/2, since there's not 1 right here, that means that I need to add in an x to the 1/2, right? And then a 2, right? So that's going to be minus 2 times 2 is going to give us 4, x 1/2, and then another 1/2. It's going to give us x squared, okay? And then all over x squared plus 1 squared. And this act of factoring out here, what it does is it allows us to write this a little bit more simply. We're going to have 1 minus 3x squared in our numerator. Then we're going to have 2 times the square root of x times x squared plus 1 squared in our denominator.